All right, Module 6, Lesson 6.2, Internal Forces. Our objectives for this one is going to be to determine the internal forces in 2D load cases. That's the internal forces and moments that are acting inside of some members. These are really important, just like it was with just axial force in those trusses. Now we're going to have more than just axial force in these multi-force members, and we need to know what the shear is in the moment. Those are the different forces that you're going to be calculating. Those are going to be what makes a material work or not, or you know, from a load point of view, or even from a deformation point of view. You're going to be taking these internal forces that you're going to be calculating in this objective, in this lesson, and when you go into future classes, you're going to be applying that to the design of materials. So this is a really important concept. Likewise, we're going to have this second one, draw shear and moment diagrams for basic loadings. It goes hand in hand with this first one. Shear and moment inside the material, they vary a lot more than, say, the axial force usually. And so having them diagrammed is very common. And so we can find those maximum values of the internal forces along the length of the member. You can see this engine hoist. We talked about this in a previous lesson. It has this black boom here that extends out from this red arm, so it can go further out. And along the red arm here, I think they have some load capacities. The farther out this goes, the lower the load capacity of this crane. It can pick up a lighter and lighter engine. And that's because of the internal forces that are occurring inside this member and inside the black extension piece, as well as inside of the other components. We have already covered those two force members, like ropes, cables, truss members, etc. This hydraulic jack here, which I'm showing right here, it's a two-force member. It's got a pin at the top, a pin at the bottom, and it just has axial compression acting on it. It just has internal axial force. That's what we've solved for so far. But some materials, some members will have more than just that. Like this gantry crane here that has a huge load hanging from it, through all of these cables here that are all on the length of this beam across the top. This beam's being loaded, and the one behind it are being loaded along their length, not just at their ends. And the loads are perpendicular to that axial orientation of the beam, the longitudinal axis of the beam. So we are not just going to have tension and compression. Matter of fact, there's probably very little net tension or net compression on this beam. It's a lot more shear and moment. But let's go back and look at this engine hoist. If I take the top beam here, the boom, and look at that free body diagram that we had developed in a previous lesson. Got a 500-pound engine hanging from the right end. It's 2 feet 8 out. I think it's the maximum extension or so. So the boom of this hoist is not a two-force member. It's going to have more than just axial force acting along its length. And what I'm saying here, how do you think the designers chose the dimensions for the black extension piece? For instance, how thick was it? How tall and how wide? How thick was the material made out of? Those are all decisions that had to be made by an engineer. And it comes straight out of these internal forces, internal actions that we're going to be learning how to calculate here in this lesson. How do you think it would fail if it did break? If this black piece were to fail, I'm sure you can imagine it would like kink here and start to hang down. That's actually a moment failure, internal moment that's happening inside the material causes the failure. If we want to make sure that this beam can resist the imposed loads, we've got to find those internal forces and moments that are acting within the member. For example, maybe we want to find the internal forces acting within this beam at point D, which is this point right over here. To do that, we would first need to determine the support reactions, at least at one end, and that's because we're going to need to cut a free body diagram. We have to have those external reactions determined, at least the ones that are going to be on our free body, because we're not going to be able to solve for the internal forces if we don't even know the external reactions. And then we cut at the point that we want to find those internal actions at. So we're going to make our cut at D. You're always going to be making your cut at the point that you want to find. We make our cut at D, and now instead of just having axial force like a two-force member has had, now we've got the shear, which we call V, and the moment M, and they're at that point. And so now you can see that we've got our support reaction that we had calculated already, and then we find the resultant of this distributed loading here, and that's here, and then we can solve for these internal actions using the same equations of equilibrium that we're used to. So in this case, we would end up with these values. So in more detail, for 2D, the possible internal actions are the normal force. That one's the one we've been doing since the beginning of the year. The shear force, which is parallel to the surface of the cut. The normal force is normal to the surface of the cut. The shear force is parallel. Why is it called V? I don't know. I think because it maybe looks like some shears. By the way, like scissors or shears, that's how they actually fail in materials, by shearing it. Think about it. They cut perpendicular to the axis, like cutting through paper. And then the bending moment, M. Okay. When you're going to make a cut, you've got to choose a side, just like before. You have a free body, you keep the left, or you keep the right, or you keep the top, you keep the bottom. Whatever it is, you got to keep part, and then you got to get rid of part. So when you make a cut, you're going to cut through the point in question, and if you choose the other side than this side, then all of those actions will be flipped. And so what I mean by that is, here's this piece right here, we're going to show over here. See, it's down, pointing away, counterclockwise. And then if I did the other cut where I only kept the right-hand side, then I've got up, away, and clockwise. And that is the internal force sign convention. So you're going to have to just kind of memorize this, but the normal force you've already known. Tension is positive. So always pointing away is positive. The shear of a cut is on the right side of the free body. See how we're cutting here over on the right-hand side. The free body is left over on the left, and we've got the right-hand side is where the cut is. If that's the case, V, the shear, points down. I know that sounds counterintuitive, but that's just the way it is. And the M, the moment, is counterclockwise. If we make our cut on the left side, this is less common, but you definitely can do it. It happens all the time. Then the end still points away, but now the shear force V is pointing up and the moment is clockwise. Okay. We cannot just say counterclockwise moments are positive. We have to say for internal force, a positive internal shear is according to this. If it's on the right, it's pointing down. If it's on the left, it's pointing up. And that's because these internal forces counteract each other. So there isn't just like the shear isn't just pointing up. It depends on which side of the cut it's on. Same with the moment. Okay. The name, you might hear this called this from time to time. It's called the smiley face sign convention. The reason it's called that is because beams, if they're loaded in this way, they bend down, so their deflected shape looks like a smile. If you flip all of these signs and make the shear negative and the moment negative, then you have a frowny face beam, like a diving board. That's negative moment. They had to pick one. It's not, I'd say that positive bending is more common than negative bending, but they're both extremely common in the world. Okay, so I've said so far, you make a cut and you follow the rules of free body diagrams and you solve for your internal forces. We do need to discuss the concept of discontinuity. Okay, instead of cutting at D like we did earlier, what if we cut at C? Well, there's this 800-pound force that's happening right there. If we're making our cut at C and we follow my 3 rules of free bodies that I've been going over since the beginning, where I say you keep the part that you're keeping, you get rid of the part that you're getting rid of, and at the cut surface, you put the internal forces that develop. All of that makes perfect sense, except for is the 800 pounds? Are you keeping it or are you not? And that's really the heart here. And I think the real answer is that you cannot cut at a point of concentrated external load. You have to cut either just a smidge to the left or just a smidge to the right. There is no way you can cut at C. To illustrate this point, let's take a free body diagram cut just to the left of point C. So I'm keeping the part that I'm keeping, the 100 pounds per foot load acting over 10 feet, which gives me a resultant of 1,000 pounds. 1,400 pound upward reaction, that's still there. And then here are my internal forces that are happening, a shear pointing down, a moment counterclockwise, a normal force pointing away, which for this beam would be 0. Sum of forces in the Y is going to give me my shear. I have 1,400 pounds up, 1,000 pounds down. I'm saying up is positive. And then I say minus VC left. My positive sign convention says that on the right-hand side it's pointing down. But when I plug it into my equation of equilibrium, I still follow that sign convention. So there's really two sign conventions going on at the same time here, right? Your internal force sign convention and your statics or Cartesian sign conventions. So I have 1400 minus 1000 minus VC left. That gives me that VC left is 400 pounds. Now, if I cut a free body just like 2 angstroms over to the right, so this one was just 1 angstrom away from that 800-pound force, so the 800-pound force was not on that free body. This one, I'm keeping the part that I'm keeping. It includes the 800-pound force. So if I do this free body, the only difference is this 800-pound force acting down. You can see that changes this shear here at point C, just to the right of point C, is now drastically different by 800 pounds. It was 400 pounds positive. Now it is minus 400 pounds. You see just how important it is, the impact of these external forces. By the way, if you notice the difference in the shear here, it's a difference of 800 pounds, which happens to be the value of the applied load. You'll learn about that a lot more as you get more and more practice with shear and moment. In summary, when you have a discontinuity, a point of concentrated force, a point of concentrated applied moment, applied load or a reaction or something, any kind of concentrated vector on the exterior of your beam, you're going to have to cut either just to the left of that point or just to the right. You can't just cut at the point. It no longer makes mathematical sense. So, how do you determine internal forces? Think about the spot where you want to determine the internal forces, because you're going to end up cutting there eventually. Maybe not right away, because you probably have to find some reactions first, but eventually you will be making your cut there. You're also going to be thinking, which side do I want to keep? There's going to be an easy side and a hard side. Perhaps, maybe it's 50-50. It doesn't really matter. Flip a coin. But sometimes you have an easy side and a harder side. If you have less forces, less reactions, less stuff going on, keep that side perhaps. So once you decide which side you're going to keep, if there's any reactions on that free body, you're going to have found them before you actually draw that free body. So go ahead and look at the overall structure, determine those reactions, and then draw your free body diagram with those reactions already determined and put on it. Then when you draw your free body, have your cut at the point where you're solving for, draw those internal force vectors, the normal force, the shear force, and the moment at the cut surface, drawing them in their assumed positive sense for the internal force sign convention, that smiley face sign convention, and then develop the equations of equilibrium just like you know how to do.